Hi there. In this video, we'll look at the first derivative test, which allows us to know if the local extrema of a function are maxes, mins, or neither of those things. Here we'll look at example 1b from the textbook, in which we're supposed to use the first derivative test to find the local extreme values of this formula right here. And our general plan of attack is to, number one, compute the derivative. Okay, in general, what we're looking at chapter 4 is what are derivatives good for? And one of the things that we can do with derivatives is figure out maxima and minima. So that's what we're doing. Number 2, we'll use the derivative to locate the critical points. Then we'll analyze the sign of the derivative near the critical numbers, which will allow us to draw a conclusion about whether those critical numbers produce a local maximum, a local minimum, or none of those things. Okay, so let's get started. All right, before we jump into analyzing the local extrema, let's actually start with just forming some general impressions about the graph of this function. This is always a good idea for any problem. So let me go ahead and just do a couple easy things. In about 2 seconds, I can know the y-intercept by plugging in 0 for x. And we get 0 squared minus 3 times e to the 0, which gives negative 3. So with almost no work, I can know that the y-intercept of this graph is negative 3. Okay, also a good idea to just think about what the end behavior of a function is. So I'm going to pick a large number, whether it's 100 or 100 million. Maybe we can get an idea what the function does when the input is big and grows bigger. So 100 squared is a big number, 10,000. Take away 3. We're still at a big number. And then we're multiplying by e is close to 2.7. This is just an awfully large number. So we're multiplying two big numbers together. The answer is really, really big. Capital big. Okay, and what that means for us is that as x gets larger, approaching infinity, we should expect the inputs to become very, very large as well, which means the graph generally goes out there. Now, as we'll see, this function actually gets big very quickly. You don't have to go very high on the inputs to produce a super large output. Okay, let's go the other way. What if x is negative 100 or negative 100 gazillion? What should we expect to see? Okay, so negative 100 squared is the same as before, and when we take away 3, we get this value. However, this time we're getting the reciprocal of e to the 100th power, and so we get a number that's kind of big multiplied by the reciprocal of a really big number, like enormously big. Okay, and we know that the reciprocal of a big number is small, so we're looking at something that's kind of big multiplied by something that's really, really small. So I'll put very small. Okay, and what happens when you multiply a big number by a small number? Well, now it's a contest. If the big number is really big, then the answers get big. If the small number is very small, then the answer gets small. And I'll just comment that this function is growing so much faster than this one that this guy wins. And the answer approaches 0. Okay, so we should expect, as our inputs are large negative numbers towards negative infinity, the outputs are going to get close to 0. And so we should expect the graph to look something like that. Here is a recap of everything I've said so far. The y-intercept is here. The right end behavior is up. The left end behavior is get closer to 0. Okay, and now we'll turn our attention to whatever happens in between, what goes on with this graph in between the ends. And that's where we'll focus now. Okay, time to do some calculus. So we're going to compute the derivative. This is a product of two functions, so we'll of course use the product rule. And here goes. We want the derivative of the first expression, which is 2x, times the second expression, plus the derivative of the second expression, which is e to the x, times the first expression. And there's the derivative of the function. Step 2. We want the critical points, which are numbers that make the derivative 0 or undefined. And this expression is going to be defined for all x, so we don't have to worry about that. But potentially, we can make the slope 0. Okay, so factoring is always helpful when you're trying to find zeros. It's just useful to factor. So I notice e to the x is a common factor in both parts of the expression, so I'm going to factor that out. And let's see what's left when I do that. I need 2x, and I need x squared minus 3. Okay, and let me continue my process of factoring. Okay. And I'm just going to organize this into standard form so it looks familiar. And we recognize this is the product of x minus 3 and x plus 1. And now we have the derivative in factored form. So we should be able to identify the zeros based on that, zeros of the derivative. When x is 3, we'll get something times 0 times something, and that gives 0. Or when x is negative 1, this term will become negative 0. And then we'll have something times 0. So the answer will be 0. And lastly, well, that's it. That's all there is. Question, can e to the x ever be 0? Let's stop and think about that just for a moment. E to the x. Let's do some point plotting with e to the x. Here's e to the 0. You get 1. E to the 1 is e. It's about 2.7. And e to a higher power gets higher. E to the negative 1 is 1 over e. It's about a third. And as we plug in values, you get smaller and smaller fractions. Notice that this entire graph lies above the x-axis. In other words, the outputs are all positive. Positive outputs. You can never get 0. You can never get a negative input. And that's true for all exponential functions, not just e to the x. Okay. So this completes our analysis of the critical numbers. We have exactly 2 zeros for the derivative, and they are 3 and negative 1. Now it's time to figure out what goes on at 3. Is there a local max there? Is there a local min there? What goes on at negative 1? Max, min, flat point? Let's find out. This is where the first derivative test comes into play. But first we're going to make a sign chart in which we'll organize the important inputs. Okay, critical numbers are negative 3 and 1. So this is just a miniature number line. It extends to infinity and minus infinity. And we're just singling out the critical numbers on that number line. All right, now I'm going to split this apart just to make it real simple and clear into its component factors, x plus 3, x minus 1, and e to the x. And then we'll multiply the 3 factors together, which gives us f prime. Have I done this wrong? This should say x minus 1. Whoops, let me fix that. X minus 1. Whoops. X minus 1 times e to the x. Okay. All right, so I'm just going to look at each factor separately and then look at their product. So let's see. Starting with x plus 3. Something plus 3. Well, if I plug in negative 3 specifically, obviously you get 0. If you plug in a number that's higher than negative 3, such as 22, you're going to get a positive answer. And it should be evident that any number that's higher than negative 3 will give a positive answer. So these are all positive in this region right here. And similarly, if you plug in a value that's lower than negative 3, like negative 10, then you're going to get a negative answer. So in here, these answers are all negative all the way out to the end of the number line. Okie doke. Okay, looking at x minus 1, we can tell it's 0 when you put in 1. And if you put in a number higher than 1, you get a positive answer. If you put in a number that's lower than 1, you'll get a negative answer. And that's that. E to the x, as we've seen, is always positive. So regardless of which value you put into the e to the x function, you're getting a positive answer every time. Sometimes very big, sometimes very small, but always positive. Okay, and now we're ready to put everything together with the first factor times the second factor times the third factor. And basically we're just using sign rules at this point. So let's see. Here are the critical numbers I'm singling out. And obviously if any one of these things is 0, then the whole product becomes 0. There we go. Again, this critical number has one of the factors 0, so the product is 0. And now we'll do the in-between stuff. So to the left of this critical number, we're looking at a negative number times a negative number times a positive number. And the two negatives cancel out, and we're left with positive answers. So I'll put positive over here. Okay. And in the in-between zone, between -3 and 1, we've got positive, negative, positive. And their product is negative. In the zone to the right of 1, we're looking at positive, 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 and their product is positive. Okay, so now we have an analysis of the sign of f prime, the sign of the slope, and now we'd like to make some inferences about the function itself and the behavior of the outputs. Okay, so we know that positive slope means the outputs are increasing. Negative slope means the outputs are decreasing. And so we should expect a local max at this point. Positive slope means the outputs are increasing. And therefore we should expect a local min at this point. All right, and let's put that into formal language using the first derivative test. Whoops. So at the output of, at the critical number, -3, we saw that the slope changed from positive to negative and is therefore signaling a local maximum. Just to the left of -3, the slope is positive. Just to the right of -3, the slope is negative, and that signals to us that that output is a local maximum. Okay, and again, this is the expectation of the College Board in terms of the AP test, that students are able to write these sentences. It's almost like a miniature essay showing the logic of derivatives and classifying local extreme values. Here goes. Okay, so for this critical number, x equals 1, we saw that the slope changed from negative to positive, and that signals to us that there is a local min at that point. So at x equals 1, at our second critical number, x is 1, to the left, the slope was, negative. And to the right of that critical number, the slope is positive. And therefore, the output is a local minimum. Okay, and let's put all this information back onto our graph, where we have just some rough details about the end behavior and the y-intercept. And so now let's go and make a note about the critical numbers, -3 and 1. And we said that this should be a local max. So the graph was having a positive slope and then a negative slope. And we expect to see a max here where x is -3. Okay, and at 1, we were expecting a local min. So it should go to a min point at 1 and come up. Slope was negative to positive. So we're expecting it to come up like that and shoot off to infinity in a hurry. Okay, so let me just connect these pieces. And there's my rough picture of the graph of this function. Again, the calculus tells us to expect a local max here and a local min here, and that was the point of this video. Let's now go to the computer and look at the graph that Desmos produces for our function. And let me just go into annotation mode for just a quick second here so that I can write on the screen. All right, so we have the function here. We have our critical number in the output, the second critical number in the second output. And you can see with that, can I make this go away? You can see with that that we were correct the whole time, that the right end behavior shoots to infinity, getting big awfully fast. The left end behavior is creeping down towards 0. The y-intercept is indeed -3. The critical number just to the left has positive slope and then negative slope. And around 1, we get negative slope, then positive slope. And we see that these are indeed local max and local min points, respectively. As far as absolute extrema, there's no max, because you can go as high as you want. Whereas this point right here, let me clean this up for a second. This number right here, -5.437, is the absolute minimum value that this function takes on. Okay, I hope this video was helpful to you in mastering the first derivative test, and we'll see you next time.